Hi, today's lesson is going to be on topic 5.3, which is about batteries or something called electric cells. Under understandings, we're going to need to be able to determine the difference between a cell and a secondary cell. Okay, and real-world cells is what we're going to be talking about here, or real-world batteries. Okay, real-world batteries utilize a chemical process and also have something called an internal resistance. Okay, this is the resistor associated with the battery. At the end of this unit, we're going to talk about two definitions, which is terminal voltage or terminal potential difference, and EMF, which stands for electromotive force. Okay. Under applications and skills, I'm not going to read them to you. You can see them on the right here. They're also listed in the IB guide. For formulas, it's pretty simple. We only have one formula this unit, which says that the EMF, which is represented by that curly backwards looking 3 or curly E, is going to equal the current in the circuit times the resistance of the circuit, that's the capital R, plus lowercase r, which is the internal resistance. From that formula, you can see that the internal resistance will be in series with the circuit's resistance. Okay, under guidance, we're going to be looking at how a regular real-world battery operates over time. Okay, first of all, there's a difference between the word cell and the battery, but that difference is pretty subtle. In application, we're going to be using those two interchangeably, and I use them interchangeably. A cell is basically just a single unit that converts chemical energy to electrical energy. A battery, on the other hand, is a collection of cells. Okay, the only difference is if you have an internal resistance per cell, the battery will need to incorporate every single one of those internal resistances in series. Okay, but in application, both of them will have a voltage, both of them will have an internal resistance. It's a question of how much resistance will it have. Okay, there's also a difference in symbology. Okay, the cell has this kind of symbol, okay? One long, one short, and again, the long side is the positive side, the short side is the negative side. A battery just duplicates that symbol multiple times. It could be once, it could be twice, it could be 3 times, okay? Or more, it doesn't really matter. It just indicates that this battery is a collection of 3 cells or multiple of them, okay? So ideally, okay, a battery should provide a constant voltage for an infinite amount of time. And that's the way we've been looking at circuits up to this point, okay? We never worried about how long that battery lasted, okay? However, in the real world, the voltage that the battery provides doesn't last forever. Anybody who ever has to charge an iPhone or a cell phone, which is all of you, pretty much realizes that, okay? The batteries run out over time. Okay, and relatively short amount of time. Okay, this is the voltage over time curve for a bunch of batteries that are generally available in the public. Okay, as you can see, the voltage pretty much decreases over time. We'll look at this graph in a little more detail towards the end. Okay, so how does a battery actually work? Okay, a basic battery has 2 different metals, in this case copper and zinc. They're fairly common choices, and they're soaked in a mild acid. If you've ever done like science fair, you could pretty much duplicate the same thing with a penny and a nickel soaked in vinegar. Okay, but anyway, the 2 metals will basically dissolve at different rates, and as they dissolve, the positive ions go into the solution, but they leave electrons behind. Okay, and that imbalance in the electrons leads to a difference in the electric potential between the copper electrode and the zinc electrode. Okay, the one with more electrons is more negative, that's the negative terminal. The one with fewer electrons is the positive terminal. It's still negative, but compared to the negative terminal, it's has a greater voltage. Okay, we call the less negative material the cathode because it is positive. The way to remember this is cathode has the word cat in it, and cats are very positive animals. You pet them, they purr. Whereas the negative metal is called the anode. Okay, it's called, and anode in this case is represents negative. You may have heard the term anion, which is kind of like an onion, which makes you cry, which is negative. Okay, and when I take the two terminals and connect them in a circuit, that difference in electric potential creates an electric field and forces the electrons to run around. Okay, they run around from the anode, remember, to the cathode. And it is this force that we call electromotive force. In reality, okay, electromotive force is nothing more than the voltage of the battery. Okay, if we just look at the voltage part, okay, it's the voltage of the battery. To calculate it, okay, we would measure the voltage of the battery when it is not connected to a circuit. Okay, from a definition standpoint, EMF is the work needed to move a charge from one terminal to the other terminal. It doesn't matter which direction. Okay, if I move it from the negative terminal to the positive terminal through a circuit, it's the same as moving it from the positive terminal to the negative terminal, okay, through the battery. The only difference there would be a minus sign, but from a loop law perspective, it's the same number, just one's positive, the other one's negative. Batteries are not the only pieces of equipment that generate electromotive force. Later in this unit, later in the year, we'll be looking at generators and solar cells, other means of generating that electromotive force to force the electrons around the circuit. For an analogy, I use the escalator analogy, okay? The battery basically takes the electrons and bumps their energy up, okay? And as the electrons then go down back to ground level, okay, that energy that was bumped up has to go somewhere. Frequently, what that energy is converted into is heat. Most of our resistors get hot. The wires get hot. Our cell phones get hot when we use them a lot. Other means, okay, it could go into light energy if it's plugged into a light bulb or an LED. It could go into kinetic energy if those electrons are then used to run a motor. It could go into sound energy if it's used to power a speaker. Okay, but as those electrons get back to the ground floor, they take the escalator back up and they keep running this circuit around and around and around. Okay, so electromotive force. Okay, why do we measure the electromotive force with a disconnected battery? Okay, the electromotive force is measured with a disconnected battery because if I have current running through that battery also has internal resistance. That internal resistance exists because of the metals and the chemicals used. Okay, remember, we've already seen that a real-world wire has resistance because it's made of metal. Same with the battery, okay? Those pieces of metal represent the internal resistance. If I run a current through there, I will lose voltage because of that internal resistance, and the battery will register a lower voltage as a result of plugging it into a circuit. Okay, but if I look at it disconnected, then the voltage that the battery has is the EMF voltage. Okay, and that's what we're going to use to represent the voltage source. Okay, just the batteries or the cell symbol in this case. So the internal resistance, because of that internal resistance, it will change the nature of our circuit. Okay, so that whenever we see a real-world battery, we need to include that internal resistance in our calculations. Okay, in this picture, okay, we see that the voltage is measured across the EMF and the internal resistor. Okay, that's the terminal resistance of the battery in the circuit. Okay, and so when I include that little r, that internal resistance, the total resistance of the circuit becomes capital R plus little r. Okay, and the terminal voltage, which is what happens when I measure the voltage of the battery in a circuit, okay, is going to be that EMF E minus that internal resistance R times the current I. Okay, so terminal resistance is going to equal epsilon minus current times little r. Okay, it's also the voltage of the circuit. Okay, so don't forget that option. Okay, I talked about secondary cells in the beginning, And the only difference between a primary cell and a secondary cell is that secondary cells can be recharged. Primary, which is similar to the number 1, okay, are basically just one-time use only. These are the batteries that you use and throw away. Secondary cells, however, can be recharged. This is the battery in your car or your cell phone. Every night when you plug it in, you are recharging that battery. You recharge it by forcing electrons the wrong way into the battery. Okay, so the secondary cells are basically utilize a reversible chemical process to recharge that battery. Okay, it doesn't necessarily recharge it up to its original, but it does recharge it. Okay, and so you can reuse that battery many times. Okay, however, even with your iPhone, okay, as you use it more and more, you notice that it takes longer to recharge, or it doesn't seem to last as long. So it doesn't get you back to 100% most of the time. I also talked about the graph at the beginning of this lecture. Okay, battery lifetime is something that the IB requires you to understand. Okay, and it basically breaks down into 3 sections. In the beginning of this battery, okay, it's been sitting on the shelf. The metals have been dissolving for quite a while, not very actively because it's not hooked into a circuit, but it has been dissolving. As such, it has kind of a built-in potential difference that's different than what it's generally in use. Okay, and that's this beginning section here. Okay, right in this section, okay, that's where it's just come off the shelf and it's being used. At this point, it's got what's a fairly steep discharge. Okay, at this, so it's basically using up the stockpile of electrons that it had dissolved in the beginning. Okay. The midlife is the general usage. Okay, this is generally when we use the battery. It lasts for a fairly long time, and it's this fairly shallow slope. It does lose voltage over time. Okay, and then we have the end life section where it's really no longer usable. It might be. It's not 0 voltage if you look. Okay, we're only talking 3 volts here, which is still quite a bit. Okay, but for the most part, if I needed it to be a 4-volt circuit, or the circuit needed 4 volts or 3.5 volts, this is no longer good enough for me, and I need to go and get a new battery. Okay, so the end life is basically represented by this falling off a cliff type of curve. Okay, a very steep discharge curve. In general, we measure a battery in ampere hours. How much current times how much time. Okay, if I use more current, then it doesn't last as long. So this is what happens when you're using your cell phone and it doesn't seem to last the whole day. However, if you just leave it sitting on the table, not using it much, it'll last a day, maybe even 2 days before you really need to recharge it. Okay, and so that's how we measure them. Okay, sometimes it's measured in milliamp hours, but generally ampere hours is a good measurement. Okay, so thank you very much.